Hi, I'm Mark Weitzman. Welcome back to Quantum Field Theory: A Student's Perspective. Today I want to do one of our first recitations. I'll solve a couple of problems in Srednicki's book, problems 2.1 to 2.3. These aren't particularly difficult, but they do involve like index gymnastics. And for those who aren't familiar with tensor manipulations and everything, you might profitably look at these. But I recommend doing all these problems, try them first before looking at these videos. And as I said, I don't like to ruin textbooks by doing the problems in the book. So from now on, I'll probably only do one or at most two problems of the interesting ones in a chapter. So today, let me start. As I said, we're going to do the recitation. Problems 2.1-2.3 in Srednicki. And so let's start with problem number 1, which says that asks you to verify that equation 2.3 implies 2.8. And when reading all physics, especially all advanced physics textbooks, one should verify every equation in the book. No matter how tedious it might seem, it will tremendously help your understanding of the material. Okay, so equation 2.3 is simply g mu nu, and just a matter of notation, Srednicki tends to use the full metric notation g mu nu that you use in general relativity for a general metric, rather than eta mu nu for a Minkowski metric. So I'm just following what he's doing here, but just remember that g mu nu is defined to be eta mu nu. So the equation that we have is g mu nu lambda mu rho lambda nu sigma, lambdas are Lorentz transformations, equal g rho sigma. That's our starting equation. And we know for an infinitesimal Lorentz transformation, lambda mu nu is equal to del mu nu plus del omega mu nu. Now del mu nu, this is just the identity matrix or the Kronecker delta. It's equal to 1 when mu and nu are the same indices and 0 when they're different. And I put parentheses del omega. Think of it as a parameter matrix. Don't think of it as del times omega. This is just a single symbol. I'm only going to do it probably once. And then these are the elements of the matrix. And what we want to show is that this matrix is in fact anti-symmetric. But it's only anti-symmetric when the indices are both up or both down. So let's substitute the lambda into here. And we get g mu nu del mu rho plus del omega mu rho times del nu sigma plus del omega nu sigma equals g rho sigma. So we just substituted this into there and into there. And that then becomes that. Okay, so now it's just a matter of plugging and chugging. I'll move this to the other side, so we get G rho sigma is equal to G mu nu del mu rho del nu sigma. I'm going painfully slowly here because I'm assuming that the people who are really watching this video are like first timers. Plus G mu nu. Now we have this term, del omega mu rho del nu sigma. So I'm doing the cross term here. And then I'm going to do the cross term here. Plus G mu nu del mu rho del omega nu sigma. And the final term is plus G mu nu del omega mu rho del omega nu sigma. But this is second order, so we're not going to worry about it, because del omega, this is an infinitesimal Lorentz transformation. So now we have G rho sigma is equal to, now all the Kronecker delta does, since we're always using the summation convention, it just says that this is 0 unless rho is equal to mu. So we can substitute for mu rho and for nu sigma. So we get G rho sigma plus, and the same thing here in this term. I have I set nu equal to sigma. So I get plus G mu sigma del omega mu rho. And then finally I get this term here, the last term. That goes to that, and that goes to that. Now this goes down here, and this is just G. Here we're going to set rho mu equal to rho. Sometimes it does it, and sometimes it doesn't. Okay. Okay. I screwed that up anyway. Okay. So subtracting here, we just get 0 is equal to G mu sigma del omega mu rho plus G rho nu del omega nu sigma. And now we just use our lowering and raising properties of the indices. 0 is equal to, by definition, when we have this G mu sigma and a upper mu index, it just lowers it down. So that becomes del omega mu rho. And then here we lower on this. So I get plus del omega rho sigma. It lowers the nu index and replaces it by sigma. So this just implies exactly what we wanted. Del omega, no, I did something wrong there. Okay. Should be sigma. So this implies del omega rho sigma is equal to minus del omega sigma rho. And that's what we wanted to prove. So that was easy. Just a matter of keeping track of indices, raising and lowering terms. Nothing deep there. Okay, so let's go on to problem 2.2. Now we want to prove that u of lambda inverse u of lambda prime is a different Lorentz transformation. That's all it means. It's not a derivative or anything like that. U of lambda, this is equal to u of lambda inverse lambda prime lambda. We want to prove that this implies equation 214. Now, first of all, let's look at this equation, ask ourselves if this makes sense. U is a unitary representation of the Lorentz group. So that's fancy language, but what does it mean? Well, we're not going to use the unitary part, but the representation part is important. And whenever you have a representation of a group, it means that U of AB is equal to U of A times U of B. That's the definition of a representation, where A and B are group elements, and U maps from the group to the operators of the group. Trying to think of the best way to say the operator group. I'll just go operators. So what this is basically saying is we can take two elements of the group, A and B, multiply them, then take the mapping to our operator. That's the same thing as composing the operators of each of the group elements. So for this case, our group G is the restricted, might not have to be restricted, but be easier, Lorentz group. And the elements are like lambda, lambda prime, etc. And the operators are the U's. U of lambda 63 is an operator. So it's important that sometimes it's confusing, but it's nice to keep clear the distinction. So let's once more write. We're going to do this from the infinitesimal. So we have lambda prime is equal to 1 plus del omega prime. I put primes. So these are the parameters for the infinitesimal transformation lambda. And then we have, in general, we have our relationship that U of 1 plus del omega for any general parameters is equal to, I'll put the identity element here, or the Kronecker delta, but this is just a definition. And so mu nu are what are known as our operators, and they're the generators are called the generators of the Lorentz group. Okay, so now let's go substitute into our formula here. We're going to substitute in just the Lorentz transformations with the parameters and just multiply everything out, and that's all that's involved. So let's do that. So we have u of lambda inverse, and I have u, I'll do the lambda prime first, 1 plus del omega prime u of lambda. This is equal to u by what we assumed, u of lambda inverse. I'm going to make use of the fact that because these are group elements and representations, it's always true that u of lambda, u inverse of lambda is the same thing as u of lambda inverse, as you can show by making use of that group representation property that I listed earlier. If we use this property, you'll be able to show that. So I have u lambda inverse, lambda prime, lambda. We need to show that this implies equation 214. You know what, that's not what. So this is u I'm going to put lambda inverse here because I'm making use of this here. Then I have 1 plus del omega prime. Then I have lambda. Okay. And now I have u inverse lambda. We'll substitute in this equation over here. We'll substitute in that. So I'm going to get 1 plus I omega over 2 del omega prime mu nu m mu nu times u of lambda equals. Now it's important to keep distinctions here. Omegas are just parameters. They're just numbers. So we don't have to worry about order or anything like that. But the m's are operators and the u's are operators. So we have to keep track of the order there. And now this is equal to u of, and we can do this multiplication. Lambda inverse 1, lambda is just going to be the identity, 1. And then I'm going to get plus lambda inverse del omega prime lambda. Okay, so let's just keep working it out. When we do u of lambda 1, u inverse lambda 1, u of lambda, that's just the identity, or 1, plus u inverse lambda know what? So I have 1 u inverse lambda m mu nu u of lambda, and the parameters are I over 2 del omega prime mu nu, and this is equal to, now we can expand this out again using our basic equation here. If u of 1 plus del omega. I can expand this out as 1 plus, the parameters are I over 2 lambda inverse del omega prime lambda. Now I'm going to put indices on this, like rho sigma. It helps to use different indices sometimes on each side of the equation, like I'm using mu and mu on the left and rho and sigma on the right. Eventually I may change them, but I just want to avoid any confusion right now. Okay. So the ones cancel, and we're left with, and the I over 2's cancel. Once the ones cancel, the I over 2 cancels. And we're left with del omega mu nu prime u inverse lambda, generator mu nu u of lambda is equal to, now I want to put indices. These are three matrices which are multiplied successfully, and I'll just put indices on the matrices. And to figure out how to do this, you know that the first index is rho and is down, and the last index is sigma and is down. So this becomes lambda inverse rho. I know that. I know the last index is going to be lambda, and there's going to be a sigma down here. And now I have del omega prime in the middle. And now I just have to, consistently add indices. So I put a u there, a mu there, not a u, a mu. I put a nu here, and I put a nu here. That makes everything good. M rho sigma. Okay. So now I have del omega prime mu nu u inverse lambda m mu nu u of lambda is equal to, now I can take the parameter out. That's why I needed to expand that. And if you notice, I chose indices so that the parameters on each side of the equation had the same indices. You'll learn, as you do this more and more, you'll learn these tricks beforehand. Now we're going to use something we've done I've noted before several times, that to get the inverse of lambda rho mu, you take the transpose and leave the indices in the up and down positions. So this becomes lambda mu rho, lambda nu sigma, m rho sigma. Okay, we're almost done here. Now we make use of something called the quotient theorem in tensor analysis, which basically says whenever you have a product of two tensors with like independent parameters, you can cancel the parameters. So here I can cancel this del omega prime u nu. There's a little bit of subtleties here because they're not all independent, because del omega 1, 2, for example, is equal to minus del omega 2, 1. But we're okay here because mu and nu are, this is anti-symmetric, and mu nu is anti-symmetric. So we're only getting the parts that count here. And the same thing is true here. If I were to switch, let's say I were to make this, del omega prime. I just want to show you that this side is also anti-symmetric in mu and nu. It's not that obvious. I get del omega prime nu u, just switching the indices, lambda nu rho, lambda u sigma, m rho sigma. But now I can switch rho and sigma. I can make rho sigma and sigma rho. So I get minus del omega prime mu nu. And I'm going to reorder these because these are just numbers. Lambda mu rho, lambda nu sigma, and then I get m sigma rho, and this becomes minus m rho sigma, and then the minus signs cancel and we get back to that. In other words, both of these are symmetric. You know, this is anti-symmetric and this is anti-symmetric, so I'm only taking the parts that count. So using that fact, I can cancel these two things, and I get u inverse lambda m u nu u of lambda is equal to lambda mu rho lambda nu sigma m m rho sigma. And this is what we wanted to show. I don't know why it did that. Okay, so let's look at this equation for a second because it's a very interesting equation. This side over here is how operators transform. And you'll always, in quantum mechanics and quantum field theory, you'll always see operators transforming as u dagger ou. Because we have a unitary transformation, this is the same thing. Sometimes they transform with u inverse. Sometimes you'll see books write them uo, u dagger. Doesn't really matter. It's just a convention. And sometimes when you're using active versus passive, they reverse. And I still haven't completely figured out the consistency among all the books, but usually this is used for some of them. That's how operators transform, and this is how second rank. What does rank mean? Rank in tensor analysis and in matrices, rank means the number of indices on the tensor. So here's two indices. So this is a second rank or a matrix tensor. And contravariant and covariant are fancy words. Contravariant just means upper index. And covariant means lower index. In this case, both of our indices are up here. So they're both contravariant indices. And whenever you have a contravariant indices for a transformation, boy, I keep touching things and things happen. I still haven't gotten a hold of this software. The general rule for like a contravariant tensor t prime mu nu is equal to the partial of x prime u with respect to x alpha, partial of x prime nu with respect to x beta, t alpha beta. So in this particular case, our Lorentz transformation is x prime mu is equal to lambda mu, let's call it gamma, x gamma. So the partial of x prime mu with respect to x gamma is equal to lambda mu gamma. So you can see we have the right things here. So it's exactly, it just says that M transforms exactly how it's written as a second rank tensor. Okay. I thought I boxed this equation, didn't I? All right. Now let's go on to our third problem. which is a little bit messier and more involved. So here we want to verify that equation 2.14 implies 2.16. Okay, so basically this is to verify the commutation relations. I'm just going to sketch them, you know. It's in the book. And so we want to show where this comes from. So equation 214 is what we just derived. U inverse lambda mu nu u lambda is equal to lambda mu rho lambda nu sigma m rho sigma. And once again, just to review, lambda will be considered infinitesimal, and we'll have it as 1 plus del omega, and u of an infinitesimal Lorentz transformation will be 1 plus I over 2 times the parameters with the generators. Okay. So once again, we just have to substitute in this equation. So I'm going to go 1 minus I over 2 del omega alpha beta m alpha beta. I'll explain the minus sign in a second, times mu nu times 1 plus I over 2 del omega gamma delta m gamma delta. Now, two things to note. Since we had u inverse lambda, we know that this is equal to u of lambda inverse. That simply means to take negative parameters. When we have the inverse of a Lorentz transformation, we just take the negative parameters. Here the parameters are del omega, so del omega goes to minus del omega. Simple as that. That's why we have the minus sign here. Now the only other thing to note when you're doing these problems is you don't want to use the same indices. Like here I use alpha beta. You might say, why don't I use alpha beta again? That violates, not only does that violate the summation convention, but you just don't want to do it because this is a sum of terms and this is a sum of terms, and you have to use different indices. So now I want to show that this is equal to lambda mu rho, just right over here. Lambda mu rho, lambda nu sigma, m rho sigma. So once again, we're going to have a 1, an m, and a 1. So that's just the same thing as m. So I get mu nu. And then I'm going to leave out these terms because these two are second order. So we're just going to ignore. And then we have the cross terms. So I have minus I over 2 del omega alpha beta m alpha beta m mu nu. Once again, the parameters, we don't care what order we put them in, but the operators, we have to keep the order. Then I have plus I over 2 del omega gamma del m mu nu m gamma del. This is equal to, now I'm going to make use of this over here for these and substitute in both of these things. So I have del omega, I have the Kronecker delta, the identity, del mu rho plus del omega. Remember, I told you a long time ago, del omega is always just one symbol. Don't think of it as del times omega. It's just del omega. Mu rho multiplied by del nu sigma plus del omega nu sigma m rho sigma. You know, when I decided to do the videos in this format, I had to decide if I was going to buy the biggest iPad possible on the iPad Pro, and I decided to do it, and I'm sort of glad I did it because I need all the room. Okay. So now let's just continue expanding. So let's work on the right-hand side here. Sorry. So when we multiply these two Kronecker deltas, they just say, since we're summing on rho and sigma, they just say replace rho by mu and sigma by nu. So I get m mu nu. Okay. And then I get plus del omega and now I'm going to multiply this term by that term. So I'm going to get I'm going to substitute del omega there and do it again. Del omega, I'm going to have a nu here and a sigma, and I'm going to substitute rho, I'm going to substitute for rho mu, mu sigma, plus, and then I have the other cross term. Okay, I did that cross term. Now I have this cross term. Now I'm going to have del omega mu rho, and then I'm going to substitute nu for sigma, m rho nu. Now the mu nu's cancel. That's good. And so I get, now working on the left-hand side here, minus I over 2 del omega alpha beta m alpha beta m mu nu. And now, because we have a plus sign here, I put a minus sign here. Minus. And now think of renaming gamma and delta to alpha and beta. So I get minus mu nu m alpha beta. So I'm just renaming this alpha, renaming this beta. Okay. Now let's go back to the right-hand side. And now what I want to do is, because the parameters have the indices down over here, these are both down indices, I want to get down indices on the parameters here, so I lower the parameters. So to lower the parameters, I use the G nu alpha, del omega alpha beta. Now you can see how that I'm also renaming them, I guess. Okay. Anyway, you can see how this, when this acts on this will be G nu beta. So I'm sort of setting sigma to beta, and so instead of, I have M mu beta, and then I have plus G mu beta del omega beta alpha. So this is going to raise the beta index. I'm going to get del omega mu alpha. So I'm also doing rho goes to alpha. So this becomes M alpha nu. Okay. Now this is a commutator, so let me write that down as a commutator. Minus I over 2 del omega alpha beta commutator M alpha beta M mu nu. Now this is equal to, now we know that the omega parameters are anti-symmetric, so I'm just going to factor them out. Del omega alpha beta times G nu alpha M mu beta minus, because there's a minus sign when that becomes alpha beta, minus G mu beta M alpha nu. Okay. Now, at this point in time, you might think we're done. We can cancel the del omega alpha beta out like we did before. That's the quotient theorem in tensor analysis, and we have our answer, and we'll notice that it differs from Srednicki's book. The answer is you can't cancel the parameters yet, because this is anti-symmetric and this is anti-symmetric. So this side is symmetric, but while this is anti, this doesn't have any symmetry. You can work it out. You can switch alpha and beta here and see if you get any anti-symmetry, and you will find that it doesn't. Not anti. We want it to be anti-symmetric because then the total will be symmetric and we'll be equating the right parts. Again, you can only cancel the parameters if they're all independent, but you have to remember that del alpha beta is equal to minus del beta alpha. So what you need to do over here is very simple, and this happens a lot. You need to take the anti-symmetric part of this. By the way, the symmetric part, when you take the symmetric part of this always vanishes, because when you multiply an anti times a anti-symmetric times a symmetric, you're going to get 0. So you're not losing anything by taking the anti-symmetric part of this. And to take the anti-symmetric part of a 2-index tensor is very easy. You know, the anti-symmetric part of T alpha beta is just equal to T alpha beta minus T beta alpha over 2. So that's what we're going to do here. So I'm going to rewrite this. I'm going to go all the way down here and rewrite this as 1/2 G nu alpha M mu beta minus G mu beta M alpha nu. So that's exactly what we have here, except we're multiplied by half, and now I have to subtract the other part with alpha when we switch alpha and beta. So I have minus G nu beta M mu alpha minus G mu alpha m beta nu. Okay? Now that would be multiplied by del omega alpha beta equals, I'm going to bring this down here. Now we can cancel the parameters because this is just a symmetric part. So now I get minus I over 2 commutator m alpha beta mu nu is equal to 1/2. I haven't figured out how to put the thing around there and move it like Jean Carroll and all the other fancy people do. I'll have to read the software here. I don't mind recopying this now. So now we can cancel the half, bring the I to the other side. I have m alpha beta is equal to I times. And now I'm going to rearrange the terms here a little bit so that it's the same way as Srednicki writes it with his, he writes it in his fancy way. And I seem to have a sign error here. Let me just see. Okay, this is plus. Okay, yeah. Okay, so it's I times G alpha mu m beta nu minus G beta mu m alpha nu minus parentheses G nu beta mu alpha minus G nu alpha mu beta. So let's just see where all these terms comes from. This one goes there. This one goes there. Minus G nu beta. This one goes there. And minus minus is a plus. That one goes there. So it's all correct. And that's the end of the problem. So nothing is involved here any more than what we call index gymnastics. And you get more proficient at this as you go around. It's just manipulating tensors and operators. And remember that numbers you can write any way you want, but the operators you have to keep the order. So I highly recommend you doing the remainder of the problems in Srednicki Chapter 2. They're all along the same lines. Some of them might be a little bit longer. But, that's the nature of quantum field theory, the calculations. I've often said in the edX courses and the quantum mechanics courses, when people have asked me how hard is quantum field theory, I said, it's not that it's much harder than quantum mechanics, it's just that it's an order of magnitude longer. A problem in quantum mechanics might be half a page, in quantum field theory it might be 5 pages. So you'll be doing, if you stick with quantum field theory, you'll be doing long calculations and a lot of manipulations, and you'll be developing new mathematical technology to do things like renormalization and dimensional regularization and all kinds of things. And it's just, you just get used to it after a while. It's messy sometimes. My biggest complaint when I was at Caltech was that no piece of paper was big enough for me. If you start doing things on several pieces of paper, you sort of lose track of things sometimes if you're not that neat as I was. I'm the sloppiest, as you can see. And if you, no piece of paper is long enough. So the advantage of this iPad is that I can just keep scrolling. Anyway, next lesson is lesson 3 on the quantization of scalar fields. So that's sort of like the beginning of our proper study of quantum field theory. We will show how you can quantize a scalar field. You can We'll talk about, I'll have a video on second quantization, a terminology that's not used much anymore. It's old-fashioned. But I'll do the second quantization of the Schrodinger equation. I'll do the quantization of the Klein-Gordon field, the scalar field, and the quantization of a complex Klein-Gordon field. And you'll start to see how the manipulations and the calculations get pretty long, but the end results end up being fairly nice. That's one of the puzzling things about quantum field theory, is that often you can do a very, very long calculation, but the result ends up being very nice. So anyway, thank you for watching. I will see you next time. Bye-bye.